and he is also passionate about science outreach and has delivered several talks on astrophysics and cosmology across India. He is also known as great explainer at Delhi University, and I was fortunate to be one of his student at Delhi University. We are fortunate to have you here with us today. Now I would like to invite Professor Patrick Das Gupta to deliver his talk. Okay, sir. I
Thank,
think.
thank you very much, Anil, for the warm and kind introduction. So let's begin the talk. Cosmology is a subject that deals with the origin, structure, and evolution of the entire universe. Of course, human beings have always been interested in the cause of creation. For example, this is a famous painting by Michelangelo, which essentially talks about how sun and moon were created by God. But we, as physicists, we would like to know how laws of physics, which is framed in the language of mathematics, how the laws of physics can describe the origin, structure, composition, and the evolution of the universe. But when I say universe, what do I really mean? Universe, as you know, is that entity which contains everything, including you, me, earth, moon, sun, etc. But when we talk about the universe from the perspective of cosmology, what we mean is look at the bigger structure of the universe. So, for example, this picture is a deep view of the universe through the Hubble Space Telescope. And here you can see that the universe is filled with these bright objects. These bright objects are called galaxies. So there are spiral galaxies, there are elliptical galaxies, and there are irregular galaxies. There are all kinds of galaxies. And the subject of cosmology is essentially how the distance between the galaxies change, where did the galaxies come about, what happens as time evolves to this galaxy. That is the subject of cosmology. And because I'm going to talk about the large scale structure of the universe, which consists of this distribution of galaxies, let me talk about the galaxies themselves a little bit. So I will go to another slide to show you some of the kinds of galaxies that we have. All right. Now let me go to another file where I will talk about galaxies. Right. So, as I said, that when you look through a very powerful telescope, like in this case, the Hubble Space Telescope, then the universe looks as though it is made up of all these bright galaxies. What are these galaxies? So here, as I had shown earlier, here is a structure. You can
Sir,
this.
hello.
Yeah, yeah.
I think your screen is not shared, I guess.
Oh, yeah. It's not visible. One moment. Now is the screen visible?
Yes, sir. Now it's visible. Okay, sir.
All right, one moment. One moment. Yeah. So, as I said, that if you look through a powerful telescope, then you would see the large scale structure, the universe, where you can see several kinds of galaxies. So, here is a spiral galaxy, here is an elliptical galaxy, and so on. So this is a slightly closed up view of the spiral galaxies, then elliptical galaxies, and so on. Let's look at the galaxies in some more detail. Here is an artist's conception of our galaxy, that means the galaxy in which solar system is there, and this galaxy is called the Milky Way galaxy. So if you look at our Milky Way galaxy from the top view, then you will find that there is a central bulge and there are these spiral arms where bright stars are formed. If you look to the side view, from the side view, you see majority of the stars are in the disk. This bulge is like the yolk of a fried egg. And then there are, of course, globular clusters that form the spheroidal part of the galaxy. Uh, these are mainly what we see in terms of the stars that populate the Milky Way galaxy. Here is another spiral galaxy, and you can see the wonderful spiral arms of this galaxy, and then there's a bright central bulge you can see. Similarly, this is another spiral galaxy where you have several spiral arms, not just two. You can see several spiral arms. And spiral arms are the region where the density of the gas is so high that young stars are formed. In between the spiral arms, the density of gas is not that high, and therefore not many stars form. And that's the reason why you don't, in between the spiral arms, the region is relatively not so bright as the region of the spiral arms. But then there are also galaxies which are not disc shaped, containing spiral arms. There are these huge galaxies which are called elliptical galaxies. And in elliptical galaxies, stars are distributed, uh, they are moving randomly and they are distributed in sort of manner where the density of the stars is higher towards the center. Then as you go out, you find that the density of the stars decrease, and that's the reason why the central region is very bright, and as you go towards the periphery of an elliptical galaxy, the brightness decrease. This elliptical galaxy is the famous M87 spiral galaxy, which was recently mapped using the Event Horizon Telescope. The central region was mapped. There's a supermassive black hole whose mass is about 6.5 billion times the mass of the sun, and you can see a jet emanating from the accretion disk around the supermassive black hole. Then here is another elliptical galaxy where you can see that there is some degree of rotation in this elliptical galaxy, because of which there is a dust lane that forms a disk while the stars are still moving randomly in the gravitational potential of the galaxy. But there is, because of the presence of some amount of angular momentum, there's a disk of dust that forms a kind of a planar region, and because it is mainly made up of dust, this planar region is also dark in color. All right. Apart from galaxies, isolated galaxies, there are also clusters of galaxy. Here is a cluster of galaxy that was recently mapped by the James Webb Space Telescope, which was launched about 3 years back. And you can see that many of these galaxies they are bound in the common potential well, and about 1,000 such galaxies are bound in the common potential well. So this galaxy cluster is called SMACS 0723. The star formation part, let me again go back to the older slide, because I want to talk about cosmology as such. Right. So, Anil, is the screen visible now?
Yes, sir. Yes, sir. It's visible. Okay, you
Yeah.
can proceed.
This is this is another clusters of galaxy which was also mapped by the Hubble Space Telescope (HST), and you can see that again there's a rich cluster containing about thousand of galaxies bound in the common gravitational potential well. This cluster is called Abell 2218. Now here you can see this rings, arch of rings. These rings are nothing but the lensed image of a background quasar. And as you know, general relativity tells us that light bends in gravity, and therefore a massive object can act as a gravitational lens. And here you can see the lensed image of a background quasar, and from the lens image you can find out that the total mass that is causing the lensing of a quasar is not just due to mass which you see, that means mass that can be inferred from the brightness of the galaxies, because brightness of the galaxies is essentially due to the brightness of the stars. There is more mass that is in the cluster than what the mass resides in stars. That is, about total mass is 100 times the mass that you infer from the mass of the stars in individual galaxies. And why is there this excess mass? What is it? It is one of the big cosmological puzzle. It's called the dark matter puzzle. Even galaxies have dark matter, and we still don't know what this dark matter is made up of. There are all kinds of theories. Some theories says that the dark matter is made of supersymmetric particles, each particles having rest mass of about more than 100 giga electron volt. Some theories say that these are black holes, primordial black holes, which form the dark matter, while some other theory says that the dark matter is made out of ultra light pseudoscalar particles weighing 10 to the power minus 20 electron volt or less. So, one of the biggest puzzle in cosmology is what is the dark matter made of? I'll come back to this problem a little later. Right. Now, how do you think the galaxies that we see, how are they distributed? And you will you'll find it very strange that all these came from quantum mechanics. All of you have been learning quantum mechanics, where particles behave like waves and waves behave like particles. In fact, the state of a quantum mechanical particle evolves according to the Schrodinger equation, from which you can derive many things. For example, you can derive that atoms and matter in general are stable only because of quantum mechanics, because the ground state energy is negative, but it's not minus infinity. That means particles cannot have any energy level. They have discrete energy level, which comes about by solving the Schrodinger equation. And all of you have exactly solved the Schrodinger equation for the hydrogen atom, and you all know that how the energy levels of the hydrogen atom, they are given by minus 13.6 electron volt divided by n square. N equal to 1 is for ground state, n equal to 2 is for next level state, and so on. But all atoms, not just hydrogen, the energy spectra, they are discrete, just like hydrogen atoms. And it is this that revealed a lot of things regarding the universe. So we all know that from the Schrodinger equation, we know that the energy levels of bound systems like atoms and molecules, they cannot be continuous, but they are discrete. And that's the reason why different elements, when you excite them by heating them or whatever it is, then from different higher energy levels they make transition to lower energy levels, and you see discrete line spectra from atoms. And you can find out in your lab what are the wavelength or what are the frequencies at which these energy spectra come about, and therefore from that you can infer the energy of various quantum mechanical energy levels of the atoms. This is very different from the spectra of the sunlight. Sunlight, for example, it is continuous. So the so-called, you have all seen what happens when a beam of sunlight passes through a prism. What you see is the continuous dispersion of the light, unlike what you see when you excite any element, any gaseous element. There you don't see continuous spectrum, but you see discrete spectrum. And this is largely because of the fact atoms, molecules are bound states, and from quantum mechanics, you can show bound systems necessarily have discrete energy levels. And therefore, when you excite them, you have discrete line spectra. But you can ask, what is this to do with cosmology? Well, in the beginning of 20th century, many people like Slipher, Humason, Hubble, what they did was they were looking at different galaxies, clusters, and they're analyzing the radiation using diffraction grating prism, so that they can find out what kind of elements make up these uh, uh, bright objects like galaxies and clusters of galaxies. All right. So different galaxies, they are bright because they have stars. And now when you take the light from these galaxies, pass it through either a prism or through a diffraction grating, you can find what kind of elements are there. You can find out the frequencies at which the emission lines are there. But now a very strange thing happened. And what Hubble, Edwin Hubble, what he was doing, he was looking at the emission line spectra of different galaxies, and he found that the lines, for example, the hydrogen present in different galaxies, you can immediately identify because minus 13.6 electron volt divided by n squared tells me different energy level for the hydrogen atom. And you know, therefore, on Earth, if there is hydrogen present, then what kind of spectra you will get. But when Hubble looked at different galaxies, he found the hydrogen lines were shifted towards the red end. That means that either these galaxies were moving away from each other, because of which the light underwent Doppler redshift, or something bizarre was happening. Hubble interpreted the shifting of these spectral lines from hydrogen or for any other atoms as though it is happening because the galaxies are moving away from us, and therefore the Doppler redshift was happening. And he inferred the Doppler velocity. And for nearby galaxies, the galaxies were moving away at a speed 2000 kilometers per second. Then there were galaxies moving away from us at speed 10,000 kilometers per second, and so on. Lo and behold, what Hubble found was that there was a correlation between this red, red, redshift and the distance of the galaxy. That means what? Further away a galaxy was, more was the redshift, or what he interpreted is more is the velocity with which it is moving away from each us. That was very, very puzzling. But then he made a very simple model. He was a brilliant guy. Today we know that actually this redshifting of lines are not because galaxies are moving away from each other, from us, or moving away from each other. There was something much more profound. I'll come to that soon. But fact of the matter is that Hubble found this correlation, is the correlation being more is the distance of the galaxy from us, more is the redshift of the lines. And since he interpreted it as galaxies moving away, and further the galaxies, more is its recessional velocity, he said, he gave a very simple model that shows his genius, of course. He said that suppose the entire universe was created in an explosion. Okay, from one point, things exploded and objects moved with different velocities, all right? And obviously, today, this happened, let's say, 13 billion years ago. Those which were flung with greater velocity will be far away, further away, and those which were flung with less velocity will not be so far away, because if the time when the Big Bang happened is about 13 billion years ago, velocity into time will give me how much distance, roughly, how much distance the galaxy would have traveled, and that's the reason why such a correlation is being seen. It's a nice model, but of course, there are a lot of loopholes in the model. What are the loopholes? The loopholes is very trivial. After all, the galaxies have masses. So they, even if there's an explosion, they will not be moving with constant speed. The gravitational force will make the velocities go less and less as they move away. Just like when we throw a ball, then initially the ball is moving away from us. If we throw the ball vertically upwards, initially the ball is moving faster from us, but as it goes upward, the velocity keeps on decreasing because of Earth's attraction. Same thing should happen to the galaxies. So this is one loophole. But this loophole is not such a big loophole. Major loophole was that there were galaxies which were moving at a velocity, let's say, look at this, 30,000 kilometers per second. But this is too high. We all know from special relativity, nothing can move faster than the speed of light. And speed of light is nothing but 3 lakhs kilometers per second. All right. And we have seen galaxies whose redshift is more than 10, more than 11. So clearly, if you interpret it as Doppler redshift, these objects must be moving with velocity close to the speed of light. But that cannot be because the galaxies are moving. There is also in between, there is intergalactic medium. So if a galaxy is moving with respect to intergalactic medium with close to speed of light, then it will create ultra relativistic shock waves that will cause gamma radiation. We don't see such gamma radiation. So something else was happening. What was that? For that, you have to invoke general relativity. So let me mention this and we'll, because it's a course of general relativity, I'll also go back to a little bit of general relativity. Today we know what this redshift is due to. As you know, general relativity tells us that matter causes curvature in the space time geometry. And this is what came out of Einstein's general theory of relativity. And long time back, around 1920s, much before Hubble, people like Friedman, Robertson Walker, Lemaitre, they had obtained solutions of Einstein's equation for uniform and isotropic distribution of matter, and they had shown that the solution said that the space-time geometry can be either expanding or contracting. Not only that, Lemaitre, George Lemaitre, around between 1922 and 1924, he had published papers saying that the universe, because of the solution, today we call the solution as Friedman Lemaitre Robertson Walker solution, FLRW. Uh, Lemaitre said that our universe, because of the solution, must be an expanding universe. Okay? Remember, this was before even Hubble discovered the fact that redshift increases with distance. All right? So, the reason why Hubble was getting that relation between more the distance, more is the redshift, is this, that what is happening is that galaxies that are far away, the light that is reaching us today, it is reaching us today because they are so far away, it is reaching us. If the distance is d, then the galaxy, what we see of the galaxy, the light started at a time d divided by c. So bigger is d, d divided by c is more. That is more and more in the past we are seeing. So therefore, the light has taken a huge time d divided by c to reach us. And if the universe is expanding, further away is galaxy, the light has taken a long time to reach us. By then, the space-time has expanded so much that the wavelength of light has got stretched. And that's the reason why the observed wavelength by the intrinsic wavelength of, let's say, hydrogen atomic lines is very large. While a galaxy which is not so far away, that means d is small, the light only took d divided by c time, that means it hasn't traveled for so big a time, and therefore the stretching of the light's wavelength, because space-time is expanding, is not that much. And that is the reason why Hubble got this correlation, is namely, bigger is the distance of a galaxy, larger is the redshift. Today we know the redshift is not Doppler redshift, but the redshift is appearing because of the stretching of wavelength of light due to expansion of the space-time. And therefore, we call today the redshift that was measured originally by Hubble as cosmological redshift. This is something which follows in general for general relativity. So let me go into a little bit of general relativity discussion. So, as you know, Einstein general relativity, the basic salient features are that gravity is not a force. Rather, what we think is gravitational force, These are actually due to the fact that space-time geometry is actually non-Euclidean. You cannot use Euclidean geometry. And why is the space-time geometry non-Euclidean? Because it leaves the energy and momentum of matter which makes the geometry curve or makes the geometry non-Euclidean. So, in other words, general relativity assures us that gravity is not a force, but gravitational effects that we see is because gravity is equivalent to the space-time geometry. Let me not go into how Einstein discovered or rather guessed the general theory of relativity. I'll just say that he realized one important thing, namely that in a freely falling frame of reference, that means a frame that is freely falling in gravitational field, gravitational force completely disappears, and this frame is a perfect inertial frame of reference. From that, Einstein developed the general theory of relativity. In other words, if tomorrow some experimentalist finds that the inertial mass is really not equal to gravitational mass, or in other words, in a freely falling frame of reference, things gravity doesn't completely disappear, then general relativity will become falsified. But up till now, all experiments tell us that the assumption that inertial mass is equal to gravitational mass, which is another way of saying that a frame of reference that falls freely in gravitational field inside gravitational force disappears, all experiments so far support this assumption. And that's the reason there is no reason why we should doubt general relativity. And as I said, general relativity has many predictions, like black holes is one of the predictions, gravitational waves is another prediction. Both of them, thanks to uh, the LIGO observatories, both gravitational waves as well as black holes. Gravitational waves have been detected directly using LIGO observatory, and the fact that many of the gravitational wave sources are due to binary black holes, the black holes are 99% confirmed because of the LIGO observatory. And today we know the Big Bang model and redshifting, cosmological redshifting of light can be completely explained by general theory of relativity. Now let me go back to the cosmology. Right. So therefore, we know that the Hubble's correlation that further away a galaxy is, bigger is the redshift. The reason is the redshift is not Doppler redshift, rather, the redshift is called cosmological redshift. It arises because the space time itself is expanding. That follows from solving the Einstein equation, that is a general relativistic equation. Whenever matter is distributed on some big scale uniformly and isotropically, then as shown by Friedman and independently by George Lemaitre, you will have an expanding space-time. So remember, what is happening is that suppose you are having baking a cake, then when the temperature is small, the cake doesn't puff up. But as the cake keeps on getting baked, it expands and the cake puffs up. But what expands is the basic dough of the cake. The nuts and the raisins don't expand. So you can imagine that the galaxies are like nuts, and the dough of the cake, the so-called wheat flour plus egg plus butter that forms the dough, that expands when you bake. So that is like the space-time. The space-time geometry expands, but the galaxies don't expand. Okay, galaxies, Earth, including ourselves, we don't expand. It is space-time that expands. So, in other words, using Einstein's theory of relativity, which is a theory of geometrical aspects of space-time, we find the entire universe is governed by the geometrical formulation of gravitation, and as though the God created the entire universe using geometrical implements like compass and the divider. This is a famous painting made by the poet Robert Blake. Right. Now, the okay, I'll first show the equation. So this is the Einstein's equation where Gij is the so-called space-time metric. Dij is the energy and momentum tensor associated with matter. Capital G is the gravitational Newtonian gravitational constant. C is the speed of light, and Rij is the so-called Ricci tensor. And I've also included the so-called cosmological constant, which Einstein had introduced for a very, very different reason. But today we know that universe is not only expanding, but the rate of expansion is increasing with time. That means there is some kind of a repulsive gravity, and Einstein had included this cosmological term lambda to have some kind of a repulsive gravity. And this is another cosmological puzzle which I will allude to later. And this is a solution which uh, people like Friedman and Georges Lemaitre, they independently obtained. So the line element that describes the geometry of the space-time is given by this. And this R of t is a scale factor, and R of t is increasing with time, telling us that the spatial part of the geometry is expanding because the R of t is increasing with time. All right. So, if there was no matter, then the line element ds square, if there's no matter, everywhere there is inertial frame, and we will only have the line element as given by special theory of relativity. It'll be ds square equal to c square dt square minus dx square minus ds square minus dz square. And the space-time, the curvature will be zero. But we know that there is matter, and when matter is distributed uniformly, that is homogeneously and isotropically, you can solve the Einstein's equation. Then you will see that the space part of the geometry, namely dr square, d theta square, d phi square, that is expanding because this space part of the line element is multiplied by the square of the scale factor. Sometimes the scale factor is also called expansion factor. All right. And you can show that there are three kinds of geometry possible. There are three kinds of geometry possible. One is the flat model or Einstein de Sitter universe. Flat meaning the space part of the geometry is flat, k is zero. The space part is like Euclidean. Because if you set k equal to 0, then this part is exactly like your spherical geometry element, dr square plus r square d theta square r square sine square theta d phi square. So k equal to 0 is called the flat model or Einstein de Sitter universe, while k equal to plus 1 is a closed universe. If k is plus 1, this r square cannot take values greater than 1 plus minus 1, and therefore the spatial volume at any given instant of time is finite. Okay, that's why it's called the closed universe. While if k is equal to minus 1, it's called open universe. There, your universe at any given time is infinite. So for both infinite in extent. So both k equal to 0 universe and k equal to minus 1 universe, at any given instant of time, the space volume, that means spatial distances, can go up to infinity. Only for k equal to plus 1 at any given instant of time, the spatial volume is finite. That means if you keep on going, you'll come back to where you started from. Okay. So there are these three different kind of topology for the universe. One of the important cosmological parameters called the Hubble parameter, which is the time derivative of the expansion scale factor, that means R dot. R dot is dr by dt divided by R. This is called Hubble parameter. And if you evaluate R dot by R today at the present epoch, then you call this Hubble parameter H0 because it's at today's time. H0 is nothing but dr by dt divided by R at the present epoch. And this H0 is one of the big cosmological parameter. Today, it is putting a puzzle. What is that puzzle? If you measure the value of H0 using the standard candles of galaxies, namely if you start using Cepheid variables and measure the distance of galaxies and find out the Hubble law using measured redshift and measured distances, the value of H0 turns out to be about 73.004 kilometers per second per megaparsec. Again, let me repeat, H0, if you use galactic standard rod and measure the value of the Hubble parameter today, the Hubble parameter's value is about 73.04 kilometers per second per megaparsec. While I will come to another phenomena when you use that, since I'm going to discuss it, I'm not going to give the details. If you use that instead, then you will find that the value of H0 is 68.4 kilometers per second per megaparsec. So there are these two different values that come about when you use two different methods. Now this is a big puzzle. After all, Hubble parameter should have only one value. How come when you use galactic measurement method you get 73.04 kilometers per second per megaparsec, while if you use the so-called microwave background radiation method, you will find that the value comes out to 68.4 kilometers per second per megaparsec. This is called the Hubble tension. Hubble tension problem is now so big that people think that perhaps there is new physics that is there to explain the problem, and we need to discover that new physics to understand, to solve the Hubble parameter. The other cosmological parameter is called the deceleration parameter Q, is defined as negative of the expansion factor R times the second derivative of the expansion factor divided by uh, uh, with respect to time. That means R double dot is nothing but d2R by dt square. Second derivative R with respect to cosmic time divided by square of dr by dt. So remember there's a negative sign sitting here. So if Q is positive, then R double dot must be negative. R double dot negative meaning that although universe expanding, but the rate of expansion is decreasing with time. While if Q is negative, then R double dot is positive. That means what? The rate at which universe is expanding, is increasing with time. And so happens that people like Schmidt, uh, Rice, Perlmutter, they discovered using Cepheid variables and the type 1a supernovae that the value of deceleration parameter today, Q0, that means evaluated today, this is actually positive. Positive meaning what? That R double dot, sorry, is negative. That means what? What they have found that Q is negative. That means what? R double dot is positive. Now, R double dot being positive means that universe is expanding and the expansion rate is increasing with time. That can happen only if there is something which causes anti-gravity. Can we give an analogy? Imagine that I have thrown a ball. So I'm am on Earth and I throw a ball upwards. So the distance between me and the ball is increasing with time. Is like expanding universe, but we all know that yes, distance is increasing with time, but the rate at which distance is increasing, namely the speed is going down because acceleration is negative. Why? Because Earth's gravity is attractive. But suppose it were to happen that I throw a ball and you find that the speed keeps on increasing with time. That means acceleration is positive. What will you infer? You'll infer that there must be anti-gravity source which is causing repulsive gravity, and this is exactly like that. R double dot measured R double dot today is positive. That means there is some anti-gravity source which is causing the universe to expand in an accelerated manner. And because of this discovery, Rice, Schmidt, and Perlmutter were given the Nobel Prize in 2012. Okay, now this is a big problem. What is this anti-gravity source? This anti-gravity source in cosmology has been called as dark energy. And one of the prime candidate of this dark energy is the cosmological constant that Einstein himself had introduced in 1915. Okay, so let me go into some pictures to tell you uh, about different universe. So closed universe, k equal plus 1 universe, the scale factor increases, attains the maximum, then again scale factor decreases. So universe starts with a big bang and ends up with a big crunch. On the other hand, k equal to 0 and k equal to 1 universe, the universe keeps on expanding. While accelerating universe, like what Rees and Perlmutter and Schmidt have discovered, not only the universe expanding, but the scale factor is increasing exponentially. Now, this is a big, big, big puzzle. What is the nature of this dark energy? All right. And so, to summarize what we have so far learned, result told us that universe began from a very dense state. That means your expansion factor R was close to zero. Not zero because uh, when it becomes Planck scale, like 10 to the minus 33 centimeter, you can't use classical general relativity, you have to use quantum gravity. So universe began from Planck scale and it kept on expanding. As it expands, because it's an isolated system, universe was very hot to begin with. And as it expands, obviously, just like when an expanding sphere, uh, as the sphere containing hot gas expands and you're not putting in any heat or taking out any heat, then the heat will inside, the temperature will keep on decreasing. So temperature decreases. As the temperature decreases, then different kind of particles form, like quarks. When the temperature decrease, they will form, quarks will combine to form protons and neutrons. As the temperature decrease, then the electron positron will get annihilated. But then when the temperature decreases to about 1000 degree Kelvin and less, protons and electrons will combine to form neutral elements, predominantly hydrogen, helium, and then light elements. And because now the atoms, neutral atoms are formed, the radiation don't get much scattering due to these neutral atoms. Radiation then completely become thermodynamically independent. That's called the relic radiation. But the still universe expanding, this relic radiation, the black body radiation, the temperature will keep on decreasing because it's an expanding ball of black body radiation. This was already predicted by George Gamow and his collaborators, but two engineers, Wilson and Penzias, they were engineers who were designing a very, very sensitive microwave receiver, and at the focus they had in fact included a very low temperature helium so that the detector was at temperature less than 1 degree Kelvin. And yet they found that no matter what they did, there was some thermal noise in the receiver. And that was nothing but the relic microwave background radiation, which is the radiation, which is the relic radiation telling us about when atoms and when protons and electrons combine to form neutral atoms, and the radiation thereafter did not interact much with neutral particles, and the black body radiation therefore got frozen. And as the universe expanded, the temperature decreased, and today the temperature is 2.725 degree Kelvin of this background radiation. 2.725 degree Kelvin corresponds to essentially predominantly this radiation is containing microwave photons, and these two gentlemen were given the Nobel Prize in Physics in 1965. And later on, many experiments showed that the spectrum of this lyric radiation was a perfect black body Planck spectrum, showing that it is indeed that which was predicted by George Gamow, Alpher, and other collaborators of George Gamow.
Hello,
Uh,
sir.
yeah, yeah.
I think we are only left with 2 minutes, so
Yeah, yeah. So, okay. So it's more important that you should ask questions, and
yes, sir.
you can see the background temperature fluctuations in different parts. There are these hot spots and cold spots, and they are supposed to be due to formation of structures. So there are a lot of things to discuss, and black body, this delta T1 tells us that the parameters, the cosmological parameters can be also inferred from that. And that is what I talked about Hubble tension, namely the black body parameters give us a value of 68.4 for Hubble parameter H0, while Cepheid variable supernova type 1a give us a value 73.04, which is causing this whole problem of Hubble tension. There are many other cosmological problems, namely, how did billion solar mass supermassive black holes get created when universe was only 100 million years old? There are many, many, many cosmological puzzles that they are waiting to be solved. And at the moment, I don't have time. It's more important that you ask me questions. Remember, you should not believe whatever I say. You must challenge me and ask any question that you have. And as I tell my students, there are no trivial questions. All questions are important.
Okay, if anyone have any question, then they can chat on the box. Okay, they can just post their question.
They can also ask me orally if they don't want to write it down in the chat box. They can ask me orally also.
Okay, sir. Okay.
Feel free, don't be shy. Feel free to ask any question you have.
Student can unmute themselves and then ask question. Please don't hesitate.
Okay, so Sabine is asking, is there an analogy or visualization you use to imagine space as a physical thing? Well, as you know, that how do we infer about space? We infer about space because when I am sitting in this room and I see a wall, and I know that I can't, from here, I can't touch the wall. So there is something that separates the wall and me. There's something that separates different particle points is what is called the space. So in physics, we know every concept is defined in terms of measurement. So how do we measure space? We say that, look, here I am, and here is that wall, and I can't from here touch the wall. If I want to touch the wall, I take a stick and find out a suitable stick so that from here I can, one end of the stick, I can touch the wall, and then measuring the distance between that tip and my hand, I know how much distance of the space is between the wall and me. And then you can sort of generalize to volume. So the empty volume is what is called the space. While time we know that the fact that different events, they keep on happening, they don't all happen at once. So when I'm talking, then first I say one word, you listen to that one word, then next another word. They all don't happen at once. So therefore, different events, there is a time interval between them, and the interval between the time can be found out if you have a oscillating pendulum or a clock and so on. So both time and space, they should be defined using measurement. That is how in physics we make different concept precise to quantitative measurement. That's the reason why numbers and mathematics play a very, very important role in defining space, time, mass, and so on. Okay, Naina is asking, yeah. So my email is simple, patrickdasgupta1 at gmail.com, and you can ask me any question, any doubt you have. Uh, Minaski is asking about conservation of energy when we are talking about cosmological redshift. Yes, so this is a very important point. Uh, you can show that as the universe expands, the different energy of particles like galaxies, the energy, the galaxy, if it is a moving galaxy, apart from the expansion, suppose the galaxy had a peculiar velocity, you can show that as the universe expands, the galaxy's peculiar velocity will decrease. Similarly, the light photon, as the universe expands, its frequency decreases, wavelength increases. That's the so-called redshifting. So clearly, photon's energy is not conserved in an expanding universe. Any galaxy's bulk kinetic energy is also not conserved. You might say, where is the energy going? The answer is the energy is what is driving the expansion. That's where the energy is going. So therefore, although photon's energy is not conserved as the universe expands because its wavelength keeps on getting increased, that means frequency is decreasing. So h nu being the energy of photon is decreasing. Similarly, the bulk velocity of the galaxy decreases as the universe expands. So their energy is decreasing, but it is that energy which is driving the expansion of the universe. Because the universe is expanding, just like expanding ball of hot matter, the temperature of matter decreases. After all, what is temperature? Temperature is two-thirds the factor of average random kinetic energy. So is the energy of the photon is not conserved, etc. Because it is that energy which is going in expanding the universe. Well, relative speeds, Akash is asking about relative speeds. So, as I said, normal galaxies the redshift is not due to Doppler velocity, it's the expansion of the space. But yes, there are clusters of galaxies. In a cluster of galaxies randomly move with respect to the center of the cluster. So if you want to measure what is the velocity of a galaxy relative to the center of the cluster, what you do is you measure the redshift of the center of the cluster, measure the redshift of the galaxy which is bound to the cluster, and then you can get a projected radial velocity of the galaxy. That's how they measure the relative velocities of the galaxies of a cluster, or relative velocities of stars with respect to the center of the galaxy, and so on. For the stars going around the center, here the redshift that is measured is a Doppler redshift, Doppler blue shift and Doppler redshift. Yeah, so Shubhas is asking about dark energy. So the main uh, way people are trying to find out about the dark energy is they are trying to uh, find what is the equation of state. I didn't have time to talk about the equation of state of the dark energy. As you know, the equation of state in thermodynamics is a relation between the pressure and the energy density. So for the dark energy, what you write is pressure is equal to some an equation of state parameter W into energy density. This W, if it is minus 1, then you know the dark energy is nothing but cosmological constant. So far, all observations about the equation of state within error bars is some 0.97 plus minus 0.05. So it's consistent with cosmological constant. But recent JWST analysis tells us that it can't be cosmological constant, because cosmological constant dark energy is the dark energy is always a constant, it doesn't evolve. But some papers have been published which say that the distributions of galaxies tell us that the dark energy is evolving with time. That means it can't be due to cosmological constant. It must be some strange matter, some strange scalar field or pseudo scalar field, which masquerades as dark energy. I hope I have provided uh, satisfactory answers.
Yes, sir. Yes, sir. So today's time is running out, so I
Yeah,
think that's all.
my advice to all students is concentrate on learning basic physics and mathematics, uh, and computational techniques, because if you want to become a cosmologist, then basic physics, basic mathematics, and computational tools are going to play a very important role.
Okay, thank you, sir, for giving great lecture.
You're welcome, Anil. You're welcome. So all the best to everyone. All the best, Anil.
Okay, sir. Thank you, sir. I
I'll
think we can.
sign off now. Take care.
Okay, sir.
Bye.
Thank you,
Bye.
sir.